Hello everyone, and thanks for watching Edupedia World videos. In this video we'll be learning about calculus, specifically the two subtopics differentiation and integration. When we learn differentiation, there are two specific aspects of which we'll focus on. There is an algebraic meaning of differentiation and a geometric meaning, which we'll see later when we'll come to graphs. Algebraically, the differentiation, also called the derivative of a function with respect to a particular variable, that's always how we calculate it, by the way, the derivative of a function with respect to a variable. It signifies the rate of change of the function with respect to that variable. So if the function varies very rapidly, then the derivative would be quite high. But if the function doesn't change at all, then the derivative would be very low. So let's see what that means in a little bit more detail. Let's assume I give you a function y equals x cube, and I want you to analyze this function. The graph of this function would be something like this. When x is 0, y is 0, and as x increases, y increases as well. Let's say I want to calculate the change in y when x goes from 2 to 3. In that case, when x is 2, y is 8, and when x is 3, y is 27. So the change in y is 27 minus 8, which is 19, while the change in x in this case is 3 minus 2, which is 1. The quantity of interest generally when we're calculating the change is the change with respect to the thing we were originally varying. So in this case, that would be the change of y with respect to x, which is written as delta y by delta x. So whenever we write delta y by delta x, what we are doing is we are taking the change in y and we are dividing it with the corresponding change in x, which causes the change in the original y. The reason we take delta y by delta x is this. Let's say there are two functions in which y goes from 8 to 27. In the first function, which is x cube, x goes from 2 to 3. But there's another function in which y goes from 8 to 27 and x goes from 2 to 2.1. Even though the change in y in both the cases is the same change is occurring in the second case when we change x by 0.1, while it's occurring in the first case when we change x by 1. So we can see that the change in y with respect to the change in x is much greater in the second case than in the first case, because as we change x by a slight amount, y is changing by a greater amount. Inversely, we could say to get the same change in y, we need to change x by a much larger value in the first case than in the second case. So in this case, the rate of change of y with respect to x would be much larger in the second case than in the first case. That's why we look at the quantity delta y by delta x. Let's calculate it for the more general case. Let's say instead of x going from 2 to 3, we were given x goes from x0 to x1. In that case, y would go from x0 whole cube, which it was initially, to x1 whole cube. Delta y will be x1 cube minus x0 cube, and delta x would be x1 minus x0. So delta y by delta x in this case would be x1 cube minus x0 cube by x1 minus x0. If you put x0 is equal to 2 and x1 is equal to 3, you get the same thing which you got before, 19 by 1, which is 19. So we've seen how to calculate the change in y when x is changed, or in other words, how to calculate the change in y with respect to x when two values of x is given. Now let's say we are given a slightly different question. The function is the same, y equals x cube. But instead of asking us the value of dy by dx, or delta y by delta x in this case, between x is going from x0 to x1, instead of this we say find the value of delta y by delta x at x is equal to x0, or let's say x is equal to 2 in this case. So at first glance, this question doesn't even seem to make sense. By definition, the change in x requires two separate values of x from which we subtract the 2 and find the change. Similarly for y. So to calculate the change in x between x is equal to 2 and 3 makes sense. But to calculate the change in x when x is 2 doesn't really make a lot of sense. So when somebody asks us this question, the best we can do is, we'll say instead of calculating the value at x is equal to 2, because we need two values, we'll calculate the values between x is equal to 2 and 2.1. But if they wanted the value at x is equal to 2, we could be more accurate and we could say we'll take x as values 2 and 2.001. Or if we wanted to be really accurate, we could take between the values of x as 2 and 2.000001. If we calculate the change in y with respect to x, which is delta y by delta x, between the values of x being 2 and 2.000001, we can be reasonably sure that whatever the person means by the change in delta y by delta x at x, this answer has to be reasonably close to that. So let's do this for the general case. Let's say I'm given the function y equals x cube, and I want to calculate the value of delta y by delta x at x naught. So the best we can do is we'll take two values of x, which is x naught and x naught plus delta x, where we'll take delta x to be some small value, and we already know the smaller delta x will be, the closer the answer will be to the actual value at x naught. So in this case, delta y by delta x would be the value of y at x is equal to x naught plus delta x is x naught plus delta x whole cube. So the change is cube. So the change in y will be this minus x naught cube. The change in x will be simply x naught plus delta x minus x naught. So we'll use the formula of a plus b whole cube. So this becomes x naught cube plus delta x whole cube plus 3x naught square delta x plus 3x naught delta x whole square minus x naught cube by the denominator is just delta x. We'll see x naught cube cancels, and whatever is left, the three terms, we see that delta x comes out common in all of those, and we can cancel delta x with those terms as well. So this delta x will cancel, this will become 1 and this will become 2. So its value comes out to be 3x naught squared plus 3x naught delta x plus delta x whole square. Right, now let's again remember the values of x we were taking. We would take 2 and 2.001, 2 and 2.00000001, and so on. And the smaller the difference between the two, that is, the closer the second value is to 2, the more accurate our answer will be. So let's take as close as we can. Let's take 2 and 2 plus dx. Now dx is a very special quantity. Whenever we want to denote a finite change in the variable x, we write delta x, which is what we've been writing up till now. Dx is simply delta x when delta x is very small. The word we use is infinitesimally small. Infinite is the opposite of infinitesimal. So something could be either infinitely large, or the inverse, it could be infinitesimally small. So dx is basically smaller than the smallest number you can imagine. It's smaller than 10 to the power minus 100, it's smaller than 10 to the power minus 1000. It is smaller than the smallest number you can imagine without it being 0. For our purposes, let's take it to be 0.000001 in this case. In that case, we know dx is such a small number, dx whole squared will be even smaller. Right, so we can neglect it compared to the other two terms. Similarly, since dx, in this case delta x, is much smaller than x naught. Remember, in this case dx would be 0.000001, whereas x naught would be 2. So dx is much smaller than x naught. If dx is much smaller than x naught, we can neglect this term in comparison to the first term as well. So the answer will be 3x naught squared. So we found out and this is what is called the derivative. The change in y with respect to x at x is equal to x naught is 3x naught square when y is equal to x cube. And this is what we mean by the derivative of y with respect to x. Remember, the change in y with respect to the change in x is given for two different values of x, for which we calculate two separate values of y and then we proceed further. But the derivative is specified at a particular value. So the derivative of x cube with respect to x means the change in x cube as we change x at a particular x naught. So the best we can do is we take that value and we take another value very close to that and we calculate the change between the two. So this would be written properly as the derivative of x cube. Now we write d instead of delta. Delta, I said, is used for a finite change. Dx is used for an infinitesimal change. So instead of writing delta y by delta x, we write the derivative as dy by dx. Delta y by delta x means we've taken two values which could be reasonably far apart. Dy by dx means we've taken two values which are as close together as we could possibly get them to be without them coinciding with each other. It's not even a real number. Dx is not really a number. It's just smaller than the smallest possible value. Right. So d of x cube by d of x is 3x square. Right. By the way, dy by dx is also written as y dash of x. Y dash of x, which is dy by dx, which is what we calculated now. We'll take the value of y at x and at another point near x, we'll take the difference, we'll divide it by x. This is the definition of differentiation. So we were looking at y with respect to s, this is f with respect to x. So the differentiation of a function f of x with respect to x, written as f dash of x, is limit dx goes to 0. You learn about limits in detail in maths. Limit dx goes to 0 means dx is as close as it can be to 0 without it actually being 0. F of x plus dx minus f of x by dx. The denominator dx is simply x plus dx minus x, the change in x. At x plus dx, the value of f would be f of x plus dx, and at x, the value would be f of x. So we take the difference between the function's value at two nearby points of x, we divide it by the difference in x in those two values, and that's what we write as the derivative of y with respect to x. Now there are a lot of standard functions whose derivatives you're going to have to remember. So here's a list of those functions. I'm going to try to derive a couple of them for you, just to show that these formulas are not really magic, and you'll be able to derive them after you've learned enough mathematics. So one formula which you're going to have to remember is the derivative of x to the power n with respect to x. Also, always remember there are two components when you're taking the derivative. There is the function you're taking the derivative of, which is y, which is in this case x to the power n, and there is the function which you're taking the derivative with respect to, which in this case is x. So this has the standard formula n x to the power n minus 1. That means the derivative of x cube by dx is 3x square, which we just saw how to calculate. The derivative of x to the power 4 by dx is, you put the value of n as 4, we'll get 4x to the power 3, that is 4x cubed. You could try to calculate this as well. I'll give you the formula how you'll calculate it. You just need x plus dx whole to the power 4 minus x to the power 4 by dx. You keep solving this, and in the end you put the limit dx goes to 0. And you need to know the formulas for a plus b whole to the power 4, and it will get tricky mathematically, but you will be able to calculate, and you will see that it ultimately comes down to 4x cubed. Right? There's another function whose derivative you need to remember, that is the derivative of sine x. So the derivative of sine of x with respect to x is cos of x. Let me just try to calculate this and show it to you. So the derivative of the sine of x with respect to x would be, you take the value of sine x at two separate values. So you'll take sine of x plus dx minus sine of x by dx, and you take the limit as That's all there is to differentiate. You just write this formula and after that it's just pure mathematics. So we'll use the formula for sine of a plus b, which is sine a cos b plus cos a sine b. So this becomes sine x cos dx plus cos x sine dx minus sine x by dx. Now since dx is a very small number, it's very close to 0 and cos of 0 is 1, cos of dx can be taken to be approximately equal to 1. So this term approximately cancels with this term. It doesn't exactly cancel, but the difference is almost negligible. So the answer becomes cos x times sine dx by dx. And this is something which you're going to learn in mathematics soon enough. When the angle is very, very small, the sine of the angle is equal to the angle when they're both taken in radians. And by default, in maths and physics, we always take the value in angles to be in radians. So in radians, sine dx by x is approximately equal to 1. And so this turns out to be cos x. So the same way you could derive the formulas for all of these. The first one, which is not written in this figure, is the one which I've told you. The derivative of x to the power n with respect to x is n x to the power n minus 1. ln x is nothing but the log of x with respect to the base e. So ln x has the derivative 1 by x, e to the power ax has the derivative e to the power ax, and you have the derivatives of the 6 trigonometric functions: sin x, cos x, tan x, sec x, cosec x, and cot x. Just by using certain trigonometric formulas, you can derive the values of the derivatives for all of these. And another important point is, right, up till now we've only seen the importance of the function being differentiated. Now I'll show you the importance of the function with respect to its being differentiated. So we know that the derivative of sine of x is cos of x. A better way to say this would be the derivative of the sine of anything with respect to that thing is the cos of that thing. So a statement which is obvious from this is, let's put x equal to another function y cube. That means the derivative of the sine of y cube with respect to the derivative of y cube is cos of y cube. This is the part in which students make a lot of errors sometimes. In a hurry, they'll take the derivative of sine of y cube as cos of y cube with respect to y, but that's not true. The derivative of sine of y cube is cos of y cube, but only if it's taken with respect to y cube. And in fact, this could be any complicated function. The derivative of the sine of tan cube of x cube plus 3x, I'm just taking a randomly complicated function, by the derivative of tan cube of x cube plus 3x. This is simply the derivative of the sine of something with respect to that particular thing, and that is the cos of that thing. So it will be the cos of tan cube of x cube plus 3x. The inside function could be as complicated as you want it to be. And if you want to calculate the derivative of this function, sine of tan cube of x cube plus 3x with respect to x, we'll do it soon enough, and all you need to do is you need to decompose the function into many standard formulas like this. So the derivative of sine of something will be cos of something. Then we'll calculate the rest of the terms, and that's how we'll proceed. So here we see that not only is the function being differentiated important, but the variable it's being differentiated with respect to is just as important. Now these are only 9 functions, but using these you can calculate the functions of a wide range of interests. So, and there are certain rules to do that. So the first 2 rules are easy enough. One of them is the derivative of u plus minus v with respect to x is the derivative. Now let me tell you what we're trying to do. We've learned what the derivative means. Now all we're trying to do is to calculate the derivative of many different functions. So if I want to calculate the derivative of u plus minus v, that is simply du by dx plus minus dv by dx. That means the derivatives simply add up. What that means is, if we want to calculate the derivative with respect to x of sine x plus x cube minus x squared, that is simply the derivative with respect to x of sine x plus the derivative with respect to x of x cubed minus the derivative with respect to x of x square. And we've seen the derivatives of all three functions already. This becomes cos of x plus 3x squared minus 2x. Right? Easy enough. The second rule, which is also pretty simple, is the derivative of ku by dx, where k is a constant, is k times the derivative of u by dx. Keep in mind here k is a constant. That means the derivative of 5 sine of x with respect to x, here 5 is a constant, right? So it's simply 5 times the derivative of sine x, which is 5 cos x. And just by using these two rules, we can calculate the derivatives of a much wider range of functions now. I could give you 2 ln x plus 3 e to the power x minus 5 sine x. So if you go back to the previous slide, you can reference the derivatives and see that the derivative will be 2 by x plus 3 e to the power x. The derivative of ln x is 1 by x. The derivative of e to the power ax is a e to the power ax, and a in this case is 1 minus 5 cos x. So now we've seen how to calculate the derivatives of the sums and the differences and the multiplications by a constant of any of these functions. There is another rule which is important, which is called the product rule. And the product rule is useful for calculating the derivatives of the product of two functions if you know the derivatives of the individual functions. And these rules you'll be able to derive very easily. The product rule is derivative of u into v by dx. Now keep in mind, this is different from the previous equation where I said the derivative of k into u by dx is k times du by dx. There k was a constant independent of x. It was 5 or it was pi or it was 360. But u and v both are functions in this case. So this is u times the derivative of v with respect to x plus v times the derivative of u with respect to x. That means if you want to find the derivative of x cube into sine x by dx, we know the derivative of x cube and we know the derivative of sine x. So the product rule says we know the derivative of the product of the two, and that will simply be x cube times d of sine x by dx plus sine x times d of x cube by dx. So it becomes x cube cos x plus 3x square sin x. Let me show you another application of this. Tan x by x square. We can write it as tan x into x to the power minus 2. So the derivative will be tan x times the derivative of x to the power minus 2, that is minus 2x to the power minus 3, plus x to the power minus 2 times the derivative of tan x, which you can reference the sheet, is sec square x. So we can calculate the derivatives of any of the product of these functions if we know the derivatives of the individual functions. The next rule is the quotient rule, and as the name suggests, it tells us how to calculate the derivatives of the quotient of two functions, and that is the derivative of u by v by dx is the denominator is v square, v times du by dx minus u times dv by dx. There is no magic in any of these formulas. Let me just repeat. You can derive these formulas soon enough once you learn limits. And finally, there is the most important rule, that is the chain rule. So first let me tell you the kinds of operations we can do with functions. We've done the four. We've done addition and subtraction and multiplication and division. For multiplication and division, we saw the product and quotient rule. For addition and subtraction, it's simple enough. You just add the corresponding derivatives. There is another combination of functions which you can have, which is a function inside another function. So for example, if you were to combine the functions sine x and cos x, These four operations would result in sin x plus cos x, sin x minus cos x, sin x into cos x, sin x divided by cos x. And we know the derivatives of all four of these. Using either the standard formula, sin x by cos x will be tan x, and the derivative of that would be sec square x, or you can just use the quotient rule for the derivative of sin x by cos x. A fifth combination of these two functions can be made, and that would be sine of cos of x or cos of sin x. Right. So let's take those 9 functions as our basic building blocks. We know how to calculate the differentiation of the sum of any of them, difference of any of them, product of any of them, quotient of any of them, and now I show you how to calculate if any one of them is taken inside another function. If you take the function of a function, and what the rule we use for this is called the chain rule, and it's easy enough. It just says that d of y by d of x is d of y by d of z multiplied by d of z by d of x. Simple basic fractions, dz dz cancels, and we get back dy by dx. But how do we use this? So let's say we want to calculate the derivative of the sine of cos of x. Now the only trick in chain rule, which comes with a little bit of practice, is how you decompose the fraction. So in this case, I'll decompose this as d of sine of cos x by d of, the only question is what do we choose to be z? We could take z to be anything, but we want to take z to be a certain thing so that we know these two derivatives. So in this case, we'll take it to be cos x. How I got cos x, you don't need to ask right now. After a little bit of practice, you'll be able to do that on your own. Now, we know the derivative of the sine of something with respect to that thing. This is why I stressed that point earlier. What you're differentiating with respect to also has significance. So the first term is simply the derivative of the sine of something with respect to that thing. If we call that thing y for a second, then it just becomes the derivative of sine y with respect to y, which is cos of y. So it becomes cos of x multiplied by the derivative of cos x is minus sine x. So it becomes minus sine x cos of cos x. Let me take another example to show this. Let's say you have the tan of ln x. You want to calculate the derivative with respect to x. So first of all, this is the tan of something. You know the derivative of the tan of x with respect to x. So in this case, you will write the denominator as this thing which is inside the bracket. So it becomes the derivative of tan of ln x by the derivative of ln x multiplied by the derivative of ln x by the derivative of x. The first term is the derivative of tan of something with respect to that thing, and it becomes sec squared of that thing. Multiplied by second term is the derivative of ln x with respect to x, which is 1 by x. Right? So this is the chain rule, and using these 3 rules plus the simple rule for the sum and quotient, you can find out the derivatives of any functions of interest. In the next lecture, we'll see the geometrical aspect of derivatives, and we'll see the opposite of derivatives, which is called integration. Thank you.